Hey guys, today we're going to learn some basic tricks for evaluating derivatives. So now we're getting really into how we can algebraically evaluate derivatives instead of either using the definition of the derivative, using a graph, a numerical table, so on. So we are going to talk about what happens when we multiply two functions together, and we can represent it by this function right here, h of x times g of x, and then we have a formula that will give us the derivative for our two functions. Now, one thing you want to make sure that you remember is that unlike the limit where you can distribute the limit to each piece, you're multiplying together, derivatives don't work like that. So h prime of x is not equal to f prime of x times g prime of x. And we have to use this formula down here. So let's look at an example and I'll show you how the formula works. Alright, so we have this function right here, x cubed, open parentheses, 2x squared plus 1. And so how it's going to work, our f prime of x is going to be equal to the first piece, x cubed prime. So we're going to take the derivative of that. I'm going to do it in several steps this time, and then next time I won't do it in so many steps. Times the second piece, but just the way it is, plus the derivative of the second piece times the first piece. So it's f prime of x times g of x plus g prime of x times f of x. So now let's actually use the power rule and take the derivative of these pieces. So this is going to become 3x squared, right? If we bring the power down and subtract 1. This one is just going to stay the way it is. Now if we take the derivative of this g of x, we end up with 4x, derivative of 1 is just 0, times x cubed. And you can clean it up just a little bit. It might look something like this. I might just leave this the way it is. 3x squared times 2x squared plus 1 plus 4x to the fourth. And you could do some more things to clean it up, but I think I like it that way. Okay, so now let's try this piece down here. So you really just need to practice problems to really get a feel of the formula, and it's just something you're going to have to memorize. There's not really any way around it. So let's try this without that first step that I included. So if we want to find f prime of x, we're going to take the derivative of the first, which is 2x, times the second, plus the derivative of the second. Remember, the derivative of e to the x is just e to the x, times the first, x squared. And then I might rewrite it like e to the x times x, and then this would be 2 plus x or something. You can simplify it a little more. Okay, so now let's talk about what happens when you have one function divided by another function. We have a restriction. This is called the quotient rule. We have a restriction that it's not going to be differentiable at 0 when g of x is 0, because obviously that'll make your denominator 0, and we'll have lots of problems. So here's the formula. This is just another formula that you're going to have to memorize. There's all these cutesy songs. I'm not really one to sing songs. So it's going to be the derivative of the first times the second minus the derivative of the second times the first, all over the derivative of the bottom squared. Now, on the product rule, it didn't really matter what order you went in because it was addition. But now, because this is subtraction, it's important that the derivative of the top is first, and then the derivative of the bottom is second. Because if not, you're going to end up with the wrong sign. All right, let's take a look at this example and see how we can apply it. Oh, Lord. Pull this down some. Okay, so we have this right here. We have a function on the top and a function on the bottom. So our g prime of t is going to be the derivative of the top. So we'll do t squared plus 1 prime times the bottom, t squared minus 1, minus the derivative of the bottom, t squared minus 1 prime times the top, all divided by the bottom squared. Alright, so now let's actually take those derivatives and clean everything up. So we end up with 2t times t squared minus 1 minus 2t times t squared plus 1 all over t squared minus 1 all squared. Alright, let's make this a little easier on me. I want to clean it up just a little more, so let's see what happens. So when I clean it up and I distribute, then I end up with, well, let's just leave it the way. Well, I guess I could do this. I could factor out the 2t, and then I'd have t squared minus 1 minus t squared minus 1 all over t squared minus 1 all squared. And then now these two squares will cancel, and this becomes negative 2 times 2t. So I end up with negative 4t all over t squared minus 1 all squared. And this is equal to, oh, I don't even remember what my function was. G of t. So g prime of t is what this is equal to. My algebra might be wrong there. If it is, somebody point it out to me later. Okay, so here we have another one. We want to find g prime of x. You actually could do this without using the quotient rule. I want to show you how to do it with the quotient rule, because we haven't really talked about the chain rule yet, and you would need the chain rule to be able to do it without the quotient rule. So g prime of x is going to be the derivative of the top. The derivative of 1 is just 0 times the bottom, which is a little redundant, but we'll write it anyway, minus the derivative of the bottom, which is e to the x, times 1, all over the bottom all squared. Right, so now we are going to, this is just going to be 1, so on the top we end up with negative e to the x, 1 plus e to the x all squared. And that's it. That one's pretty simple. So this just requires a lot of practice. Just making sure you keep up with your negatives, you are keeping up with all your algebra, and so on. Okay, so now let's talk about what happens if you want to take multiple derivatives. And these are what we call higher order derivatives. So I've got some notation for you. This will be helpful so you can kind of understand what everything means. So one way to write notation is like this. So there's f prime of x, right? That's a first order derivative. F double prime of x would be a second order. This just means you would take your function f of x, take the derivative, and then take the derivative again. Sorry about that. All right, so what about a higher order than that? So what if you wanted the fourth derivative? Well, it gets complicated if we start writing, 4 of those right there. So we put a little parentheses and we write a 4. And this would be a fourth order derivative. Okay, so now let's talk about Leibniz notation. So if we want to take a second order derivative in Leibniz, and we want to use Leibniz notation, it becomes d squared y, or d squared f, all over dx squared. And this would be your second. And if you wanted third, fourth, fifth, say we wanted a fifth, and this would be d to the fifth y, all over dx to the fifth. And that would be a fifth order. So this is kind of a neat example. This says, how many derivatives will it take for my function f of x, which is a fourth degree polynomial, to equal 0? And so I'm going to show you how it works. We're going to take however many derivatives it takes for it to equal 0, and I can show you a little formula. All right, so let's start by taking the first derivative. So I'm going to do this fast because you guys know the power rule. All right, and here's my second derivative. 12x squared minus 50 right? Here's my third derivative. Here's my fourth. Huh, I said fourth. And I wrote 5. I'm getting close. And here is my fifth. So it took me 5 derivatives to equal 0. Derivatives. I ran out of room. And so what you can do, if you have a polynomial, the number of derivatives it takes to equal 0 is always going to be your degree minus 1. And what happens whenever you differentiate a polynomial, so I'll write this down for you. When you differentiate a polynomial, it always loses a degree. Just 1. So if you differentiate all the way down to 0, that's going to be a constant because that would be x to the 0th power, and then it takes you one more derivative to equal 0. So one of the neat things you can do with higher order derivatives is you can talk about the relationship between position, velocity, and acceleration. So if you start with just a position function, say we start with height, and you take the derivative of height, this is your velocity because this is the rate of change of height with respect to time. All right, so this is our velocity. So if we want the rate of change of velocity with respect to time, this is the derivative of velocity, which gives us acceleration. So we're going to see how we can apply this. So we have a equation that models the height of a helicopter, and we want to find the acceleration at t equal 5 minutes. So we are going to take the first derivative of height because that's my velocity, and this is just going to be 300 minus 12t. Now we are going to, this is velocity, right? So now we're going to take the derivative of velocity, which is the second derivative of height, and we get, oh sorry, it should be negative 12t squared, and we just get negative 24t. So if I want the acceleration at t equal 5 minutes, this is just h double prime of 5, or a of 5, which is going to be negative 120. Remember the units for acceleration. It's going to be meters because that's what I'm measuring my height in. And then my time is in minutes, so it's going to be meters per minute squared. So let's see if we could plot the acceleration, or just kind of an idea of our graph for acceleration between 0 and 6. So I didn't label this. Let's label this. So I know it's going to go through. If here, right here, remember, is my formula for acceleration. It's just linear. It's going to have a slope of negative 24, y-intercept of 0. So it's going to look something like this. From 0 to 6. That's my guesstimate, right? And then what could we say about whether or not the acceleration is increasing or decreasing? Or I guess whether or not the velocity is increasing or decreasing. So we could say that our velocity is decreasing. So we're actually slowing down. When t is between 0 and 6 minutes. Because my acceleration is negative, if you have negative acceleration, then you are slowing down. Okay, so we've got higher order derivatives, right? Just keep taking derivatives. We got the notation. Understand the relationship between position, velocity, and acceleration. So now let's talk about the last one with piece that we're going to talk about today, which is trig derivatives. These, unfortunately, are just another group of things that you have to memorize. Got them all written up here for you. So um, you should really look at some of the proofs as how these come about, because this is really, really neat how all of these derivatives relate with their original functions. Um, so there's not much we can do other than just manipulate them. I mean, so let's take a look at this first example. So we want to find the equation of the tangent line at x equal pi over 4. In calculus, generally, we're always in radians because they're unitless. I would say unless it specifies, you should always be in radians. And then for y is equal to sine x. So we want to take the derivative of y. Derivative of sine is cosine, so that's going to be cosine x. And then we want to evaluate it at pi over 4. So y prime of pi over 4 is cosine of pi over 4, which is root 2 over 2. So this is going to be the slope of my tangent line, right? And now I want to find my original point. I know at x it's pi over 4, but I need the y value so I can write my equation. And this is just going to be sine of pi over 4, which is just root 2 over 2 also. So now let's write our equation. So y minus y1 is equal to m times x minus x1, right? So let's plug in what we know. So we have y minus y1. My y1 was root 2 over 2 is equal to m, which was also root 2 over 2, times x minus x1, which was pi over 4. And there's my equation. It's so nasty, I don't really want to clean it up. You can if you want. Okay, let's try another one. So here we are going to take and we're going to use the quotient rule because, right, we have a fraction, one function on top and one function on bottom, so we can apply that. And we can also use our trig derivatives. So let's see what happens. So I want to find f prime of x. So the derivative of tangent is secant squared. So let's see what happens. So if I take the derivative of the first piece, that's going to be 0 plus secant squared, so that's secant squared x, times the bottom, minus the derivative of the bottom. So my tangent is negative, so this is going to be negative secant squared x, times the top. I ran out of room, but I think you can get the idea. Now we want to divide by the bottom squared. And now let's see if we can clean up a little. So this is going to become plus right here, right? Because that's minus minus. So I think I'm going to factor a secant squared out because it still looks pretty nasty to me. So secant squared x is going to be 1 minus tangent x minus 1 plus tangent x. Oh. All over 1 minus tangent x all squared. And now let's see what else. So this is 1 minus tangent x minus 1 minus tangent x. So the ones are actually going to cancel. I'm going to end up with 2 negative tangent x's. So I'm going to combine those together, and I get secant squared x times negative 2 tangent x all over 1 minus tangent x all squared. And this is my f prime of x. So I think that's good. I think that's as much as I'm going to clean it up. So I think the best you guys can do is just keep practicing and practicing, and I will see y'all next time. Thanks.